Hi, our topic is QLED, quantum dot light emitting diode. You may heard or not heard this before, but you may seen some Samsung's advertisement about brighter, sharper color of QD-LED. However, this technology is not the total renovation from the traditional LCD display. They use QD films to enhance the LCD display technology. The QD enhanced LCD shows a wider color gamut of over 100% NTSC color standards. Before you get to know the true QLED, let's introduce something about LED first. LED stands for light emitting diode.
The basic structure of LED is the p-n junction. P-n junction refers to the junction formed by two semiconductor regions doped by opposite materials. When the p-type materials and the n-type materials are joined together, the mobile charge carriers tend to diffuse from high concentration area to low concentration area. The holes in p-type side diffuse to n-type side. Similarly, mobile electrons will diffuse from n-type region to p-type region. As shown in this figure, the immobile ionized atoms are left behind by diffused electrons and holes near the junction. They create a region of positive charged donor atoms in n-type side and a region of negatively charged acceptor atoms in p-type side. These two regions, we call them together as space charge region or depletion region, generate a built-in electric field in the p-n junction. The built-in electric field causes the drift of electrons from left to right and holes from right to left, in the opposite of diffusion direction. Once the diffusion current is balanced by drift current, the junction is set entering thermal equilibrium. Besides the structure, we now introduce the lighting mechanism. The emitted light comes from recombination happened in depletion region. Recombination is the process that an electron occupies the empty state associated with holes, annihilating the electron-hole pairs. There are three types of recombination, but the only one recombination process that can release light is band-to-band recombination. If the material of the p-n junction is direct semiconductor, an electron goes directly from conduction band to valence band and annihilates the holes. The lost energy is released in forms of light and heat. This type of recombination involves both electrons and holes, though the recombination rate is proportional to the density of both electrons and holes. At thermal equilibrium, the net recombination rate is zero. As the result, only when the density of electrons and holes exceeds the intrinsic carrier concentration, the net recombination is positive. Represented by this equation, the lightning intensity is proportional to band-to-band recombination rate, and this rate is equal to B times the difference of NP product and Ni squared. The B is molecular recombination constant. Maximizing recombination rate is the first goal of designing an LED. As in p-n junction, p-n homo junction is made by the same materials in both sides. This kind of LED has undesirable low efficiency because the built-in electric field sweeps the minority carriers through the depletion region very quickly, preventing recombination of carriers. p-n heterojunctions solves this problem by adding a different material between original two sides, in order to make an energy trap at the middle to catch minority carriers.
Now let's go back to the new device, QLED. The scientific fundamental of QLED is the quantum dot. Quantum dot are nanocrystals, which is defined as the type of particles that have at least one dimension of 100 nanometers or even smaller. So on the left side picture, you can see that for a typical quantum dot, the size of it is from 2 to 10 nanometers diameter. And the general structure of quantum dot is the core shell structure. So here we have a periodic table. The quantum dots are generally made of 2,6 semiconductors such as zinc oxide or 3,5 semiconductors like gallium arsenide. We have a density of states versus energy graph for different dimensions. The quantum dot are considered to be zero dimension, and the energy of it is discrete. And the energy is a function of quantum number in Planck's constant and the effective mass and the size of the quantum dot. So the energy of quantum dots is inverse proportional to the size of it. For photoluminescence, the photon come in and the electrons in the valence band got excited and jump into the conduction band. And then the energy is released in the form of light. While for electron luminescence, the electrons in the valence bands gain energy from the electric field and jump into the conduction band. So the color of the lights that are emitted is controlled by the energy gap of the material. So we have the formula here that the wavelength is inverse proportional to the energy gap of the material. So for smaller energy gap, the wavelength is longer, and a different wavelength we have different colors. And here we have the band diagram for bulk semiconductors and the quantum dots. For bulk semiconductors, the energy differences between the valence band and the conduction band is the energy gap, while for quantum dots, the energy difference between LUMO and HOMO is the energy gap. And the LUMO stands for the lowest unoccupied molecule orbital, while the HOMO stands for the highest occupied molecule orbital. So there are some important properties of the quantum dots. As we talked about before, the band gap of the quantum dots is inversely proportional to its size. And so we can control the size of the quantum dots and have a different light color generated. And we also discussed the photoluminescence and the electroluminescence. And for quantum dots, it has a wide absorption band and narrow emission band. And due to the core shell structure, it has high quantum yield. And now let's move back to the device.
QLED is basically the same as the traditional inorganic LED. Difference here is the emissive material is changed to quantum dot, so QLED inherit many characteristics from QDs. This is a green light QLED fabricated in the lab. Let's take a closer look. The forward structure of QLED contains immaterial electron injection layer, electron transporting layer, and the QDS emissive layer, and the p-type material for hole transporting layer and hole injection layer. This is a band diagram of bright light QLED. The holes are injected from the HOMOs from the left side and the electrons are from the LUMOs from the right side. They were combined at the QDs and a very sharp light is emitted. This device adopts the EL characteristic of QD. The full width half maximum can as sharp as 20 to 40 nanometer. The research for QLED is still under the lab stage. Commercial EL-QD product is not currently available on the market. The Samsung and other QD LED TVs are now just utilizing the QD's PL property. Why the QLED has so many advantages and still we cannot see them on the market yet? There are certainly some challenges. Firstly, because of the environment impact. Most QD now are containing cadmium, a toxic heavy metal. Some European countries even banned them for entering the country. The researchers trying to find some cadmium-free QLED. There is already indium phosphide QD materials available on the market, but the color is very limited. Second, because the current fabrication process is not very mature, it is still very expensive to buy the QD-based product. Thirdly, because the blue QD is much smaller than that of red QD and green QD, there are many problems of blue light QLEDs concerning their stability, quantum yield, and efficiency. Alright, hope this video can give you some idea about QLED, and thanks for listening.